Good afternoon. My name is Vaman Kulkarni. I was ex-director of mechanical systems in Honeywell Technology Solutions. I just took an early retirement a couple of months back from Honeywell. As part of the mechanical systems group at Honeywell, I was responsible for additive manufacturing initiative. We set up a state-of-the-art lab in Bangalore for metal printing. That has been my involvement in additive manufacturing for the last 6 years, and we make a significant progress in developing the additive manufacturing technology. Before joining Honeywell, I was with DRDO, a gas turbine research establishment, for 21 years, involved in developing the gas turbine engine, Kaveri engine for LCE applications. That's my brief background. Today's topic is additive manufacturing applications for prototype tooling and part repair. This has been one of the key areas where additive manufacturing has been very widely used. In fact, that's what I like this staircase uh, model from Renishaw, which shows that at the bottom we have the rapid prototyping tooling. That's where the application of additive manufacturing started way back. And with the lot of improvements which have happened in the metal printing, it has taken a much different shape in taking advantage of the functional prototypes, the tooling, and then the part repair applications. It's across the industry. It could be in the aerospace, automobile, or in the medical. So it's across the field. It has been a significant part of it. Uh, Additive is also today used for a lot of production applications, whether it could be a direct part replacement or consolidating the parts or doing a new product development as part of the as a design for additive manufacturing benefits what additive brings in. As part of the prototypes, uh, typically the name rapid prototype has been very widely used for last 20-25 years. But rapid prototype need not be always with additive manufacturing. So the rapid prototype means that how quickly we can make the prototype and then quickly do some of the functional checks, and which helps to finalize the design very quickly or do some design iterations. That's when the prototype has been very widely used. uh, uh, Additive plays a very big role as part of this new product development to uh, do the quick design validations, and it reduces the overall product cycle time. uh, Prototypes are also used for a lot of visualization checks, and especially from the assembly and maintenance point of view, the user experience, how it is easy to assemble and maintain it. So that's the other thing which we can verify. Uh, it's also used to provide the early customer demo of parts so that he can use it for the next assemblies as well as a lot of functional tests. And today, in fact, it's also used for a lot of field trials. As far as the tooling is concerned, with especially with metal additive manufacturing, it has been playing a big role in developing manufacturing tools, especially the casting and forging molds and dies. Uh, we, it helps to come out with a more optimum design of dies and molds, which will have a better cooling, and it will help in having a better quality of the part, as well as in increasing the life of the tool itself. And it also reduces the downtime because the tools can be quickly made with additive manufacturing. And lot of tools which are required for assembly and assembly requirements could also be done through the additive. And in quite a few instances, when the part is being tested, a lot of test tools or test fixtures needs to be developed in a very short period of time. So additive definitely have the advantage of supporting that. Uh, so the part repair has been in existence for last 20 years, but most of that because of the direct energy deposition using the laser technique. But with DMLS coming up in a big way in last 5 to 6 years, it's been very widely used across the industry to repair the worn out parts, as well as last minute any design changes could be incorporated very quickly onto the part which is already manufactured. So those are the benefits which additive brings as part of part repair. So we will look into the in all these three areas where this additive technology is and then how it is being applied, and there are some good examples which we have deployed additive manufacturing in all these three areas. So, before we get into that, what benefits additive manufacturing brings? When I talk about additive manufacturing, mainly our focus is on uh, metal printing. That's been our main focus. So, definitely, the advent of metal printing, we are able to design a very complex parts. Uh, with additive, which helps in improving the performance, life, and it could be lightweight. So those are the things which additive manufacturing enables, whether it's part of prototype or it's part of the tooling or the part repair. It also empowers the designers to consolidate the parts into a single design, it removes the lot of constraints which used to be there while designing a part, keeping the manufacturing constraints. So most of that is eliminated because of the process of additive manufacturing itself, which is building the part layer by layer. Additive definitely reduces the cycle time because there is no need for the tooling, and we can assembly time is also reduced because we can consolidate all the parts. Uh, it's an ideal solution for very complex parts and which where there is a low volume, which is the case with prototypes. And there is no lead time involved to get the materials because the powder which is used is already either in stock or we can get that powder very quickly. Uh, because of the process itself, there is no wastage of material as far as additive manufacturing is concerned, and it can come out with very light designs. The lighter designs could be because of using the thinner materials, or it could be because of the lattice structures. So we can come out with a very light part from additive manufacturing. Uh, Typically, when you want to get a prototype manufactured, we always go to our suppliers who can do this at a low cost. And with additive manufacturing, we can have this done very close to the either the internal customer or the external customers, where it will get into the next assembly or testing, because there is very less labor content involved as part of this, and it also reduces the transportation cost and time. Uh, the additive manufacturing process itself is very agile. Very late design changes could be incorporated very easily, and the part can be produced. So we can be more responsive to the customer changes and customer request, and we can incorporate that into the designs. So all these benefits will definitely help as you get into the prototypes or for tooling or for the part repair. There are quite still a few challenges additive manufacturing technology. These challenges could be in terms of achieving the final accuracy, dimensional accuracies, geometrical tolerances, the surface roughness. All this is decided by the powder size, the quality of the powder, the layer thickness. So it still needs some sort of a post processing to address the final finish. But still, it could be done much faster than the conventional. But these limitations still exist. Similarly, the quality of the part which is built, that still needs to be consistent and reliable. The quality of part is affected because of the residual stresses or because of the distortions which could happen while printing. So these things cannot be accurately printed. So it needs to be validated, especially when you're building a larger overhang parts. So there could be some warping issues which needs to be addressed and needs to be adopted, and supports could be need to be optimized. So there is still a manual intervention and some sort of a trial which needs to be carried out. There is still limitation on the size of the part what can be printed. The 400 millimeter by 400 millimeter is now very well established, but there are machines which are now available which can build up to 1 meter length, breadth, and height, but it is still being validated. So as time progresses, I think the size will grow as part of the additive manufacturing. Not all materials can be sintered with the today's technology. So we still have some limitations. We may not be able to print magnetic materials or the hard tool steel. So there is still a constraints as far as the material is concerned. So as I mentioned earlier, we still need to do a lot of post processing. The minimum post processing for any part which is built on an is to go for the stress relieving, and then some sort of a surface finish process. Either it could be shot peening or chemical etching to improve the surface finish. On need basis, depending on the criticality of the part, we may have to do the hipping. Hipping is the hot isostatic pressing process, which will remove the porosities, and then it increases the density of the part, and hence the better material properties. Depending on the dimensional accuracies, we may have to do some post machining. So those are the aim challenges. I just wanted to keep it upfront before we get on to the details of applications of prototype tooling and then the part repair. So this typical rapid prototyping process is what we shown here. So we get a concept design, and then the concept design is converted into a build. The build could be out of additive manufacturing, or it could be out of conventional machining, or it could be out of casting. So that's where we need to identify the right process so that we can reduce the cycle time, and then that is what is reviewed. When you say review, it is the design is validated for the performance, for the assembly, it will undergo some of those trials as part of the review, and then you go back and then refine the design, and then you do some iterations to finally have a build which can get into the production. So this is in nutshell how the rapid prototyping process looks like. It could be the prototype could be for the proof of concept, or it could be a demo model for the customers, or for the both internal and external customers, and then it also gives a visual feel of the things, and then you can also validate all the functionalities for which the product has been developed, and it could be also for the aesthetic purpose, how it looks like, because that plays a big role when you have to get the product into the market. Or it could be the initial test builds which you release it like an alpha or beta versions. This could be for the hardware or software. The word prototype is applicable across. So in our scenario, we specifically are looking at the mechanical parts as our focus. What benefits the AM brings it when you look it for the prototypes? Uh, One of the key thing what AM enables is the quicker performance evaluation. So we can have the design converted into a product which we can do all the functional tests, whether it could be at higher pressures or temperatures. Even if you are not using the original material, it can still meet it can still be tested for all those functionalities. It may not withstand the life for which the product is to be designed, but it can still be evaluated for all its performance. So that helps to quickly validate the design and then do the design improvements and then quickly build the parts and test it. I have few examples where you can see that how it is really reducing the cycle time by more than 70%. AM is definitely a cost-effective solution for building the prototypes because it's a completely automated process. There is very less labor involvement in building building the part, and of course there are no tools are required. Uh, and it's we can get a complex parts with an extreme precise dimensions because it's directly converted from the CAD models. Material wastage, as we talked earlier, it is very nil. And any risk involved in the manufacturing, so those risks can be very easily addressed and it can be quickly solved using additive manufacturing. Because as I told, the last minute changes can still be included into the design before we start actual printing. Uh, we can take these prototypes quickly to the customers or the board members and then get quick approvals for the full development of the product. Uh, it also helps to any inputs which comes from the customers very late in the design phase, and then we can incorporate that into the prototypes and then we can validate it. So it really has that flexibility to produce the parts. The applications of prototypes, I talked about the new product development. It plays a big role. We can do the very quick design validations. Design for assembly, we can validate the assembly checks. We can take it to the customer demos and any maintainability related things from the user experience point of view. All that can be validated very easily with these additive prototypes. Uh, Sometimes we need the prototypes to take it to the customers, which helps our marketing and then the sales channel to win the businesses. So we can quickly modify the existing product for the new opportunity, and then we can quickly engage with the customers to so that helps in the whole business win process. Uh, it also gives a lot of inputs when we start preparing the bids, both for the technical as well as the commercial part piece of it. Uh, uh, we can use these prototypes to have both the technical feasibility as well as the commercial validations. Uh, we, Even before we engage the final engagement, we can give those demo pieces to the customer so that he can evaluate it and then get the confidence of the customers. In many cases, whatever field failures which we see in the field, we struggle to find out the root cause and then come out with the corrective actions. So if you are able to reproduce the failure what you see in the field, then we can come out with the design fixes. So the additive manufacturing prototypes helps to quickly make those prototypes and reproduce those failures, and then incorporate those design changes, test it, and then validate it. Uh, we can also use the prototypes for the pre-production field trials, which helps to make sure that it functions properly in the bigger assembly scenarios. Uh, in some cases, there is a need to upgrade the existing part through additive manufacturing because of various concerns and issues. It could be because of the supply chain issues where we have some tough time with the suppliers, or the tooling which is involved is gone bad, and then there is no tooling drawings available. Especially this is true in an aerospace scenario where there is a long life for the product. Typically, most of the aircrafts have a life cycle of more than 30 years. In such a situation, for the parts which are 20 to 30 years old, we may lose the inventory of the tools to manufacture the parts. So for we can there may be a requirement to replace those parts with the additive manufacturing. And in some situation, because of the longer life cycle, we may want to reduce the cost of the product because the design, which is old design, has gone through a costly manufacturing process of maybe a casting or a forging. So it may be in the present technology, it is easy to either do it through the additive or do it through the hog out. So we can do those design validations with these prototypes. And in some cases, the part could become obsolete either because of the material itself or because of the older manufacturing process. So those are the areas where additive brings a lot of benefits and advantages. So in the next few slides, we will see few examples of prototypes and how it is benefiting the industry. You can see here a high pressure turbine blade. Typically, most of these high pressure turbine blades have a complex airfoil, as well as they need to be internally cooled to withstand the very high temperatures. So when we use the uh, the design process for these things, doing all the thermal analysis, the flow analysis, the CFD analysis, and come out with a design. And to manufacture these blades, it could take anywhere from 6 to 9 months to manufacture these blades, and then you have to test it, and that could take another 4 to 6 months for the testing, and then we further, if you have to modify any design changes, it's a cycle of 1 to 1.5 years what we are talking about. Typically, to finalize this type of a design, it takes about 3 to 4 years to finalize the design. But with additive manufacturing, we can have this part available in less than 8 weeks. And this one was specifically with Honeywell. We went through 4 design iterations. And in those 4 iterations, we could validate the design, and then finally, the the final production is not done through additive, but the prototypes are done through additive, and then all the validations are done, and the test, and then it is released for production. So it has reduced this cycle time from 3 years to about 6 months. The entire 4 design iterations what you are talking about, and the cost savings is also more than $500,000 as part of this product development. So same thing with the high pressure turbine nozzles. You can see the complexity of the part which is involved. So it is used additive is used for prototyping. It can finally be a process for even for the production version, but that also depends on a lot of validations and the certifications which is involved. The next one is the Toby nozzles. Toby nozzles is the tangential injection for of the cooling flow on the turbine blades to at the right pressure and temperature. So that's a criticality of these Toby nozzle designs. So we could quickly get these things manufactured through the additive, and we can take it to the testing. So the one which is printed through additive may not have the life what we are looking at, but we can take it to the next assembly like engine testing. So we can do those validations even at the engine level. So that way, the overall cycle time for the overall engine development we could reduce it. So if we had gone to the conventional approach to make these parts available, it could have taken around 9 months. So all in all, there are quite a few other models what you can see here as part of the prototyping. The typical cycle time in an industry what we can reduce is close to about 70%, and we can have a cost reduction of about 65%, and then we can do more design iterations and have a defam things completely addressed through the additive manufacturing. So in many cases, we don't make the prototypes with the actual material. We can make it out of polymers or the plastics. So there are some examples which I'm showing it here. On the right hand side, you can see that this is for the solenoid. The coil winding is the critical thing for the solenoid. We can do the winding trials with on the bobbin of a polymer bobbin, and then do all your winding trials and then finalize it, and then reproduce that on the final part also. Similarly, you can see and on the limit switch where the PCB assembly is stacked, and you need to check those quick assembly trials, and also we could quickly make a plastic parts and then assemble it and then check it and finalize the design. So that way, we, if it is although it's a non-functional part, but it helps in finalizing the design from the assembly and design validations. Coming to the tooling, so tooling is another big area where additive can play a big role. Uh, yeah, the reason why uh, the tooling application is very is wide for additive manufacturing is uh, the the tooling is not getting into the final product as so we don't have to can keep the tooling design in mind, considering the overall product applications, and then there is no need for any additional qualification of the certification of the tooling itself. Similar to the prototypes, but most of the cases, the tooling what we talk about is the tools which are required either for the molds or the dies in a casting or a forging process, or the tooling could be for the assembly fixtures, or even when you are doing the conventional CNC milling or drilling, you need to have those fixtures to hold the part. So you may require those tooling, and some of those tooling needs will come requirement will come very late, and it could take time if you go through the conventional approach. Uh, and in many cases, the tooling will decide the quality of the end product. And to have to address that quality related issues, the tool needs to be very efficient, so that quality of the final part is not affected. So, in a molding industry, typically we have two types of tooling. One is the direct rapid tooling. In the direct rapid tooling, the entire mold assembly is produced through the AM process. Uh, the rapid tooling could be completely done through a conventional process, or it could be done completely through an additive manufacturing process like DMLS or SLS, or it could be hybrid. Typically, the hybrid process takes advantage of both conventional as well as the additive manufacturing, so that we get the optimized tool done, both in terms of cycle time as well as the cost. In the indirect rapid tooling, we are not making the complete assembly. We have more than one intermediate steps in manufacturing the core and then the cavity. Uh, so that's the indirect way of the indirect rapid tooling. So there are two examples I have shown in the bottom. The first one is a cooled insert, uh, which is done through the hybrid process, and then it also incorporates the conformal cooling, so that we reduce the cooling time for the mold itself. So the complex part, which is on the top, what you can see here, which also has the conformal cooling. So that is the one which is done through the additive manufacturing. The bottom one, which is much easy to machine, that is what is done through the conventional process. Similarly, you can see here an example of an intricate mold, which could be done through the conformal cooling in a much better way, which reduces the cooling time as well as uniform cooling, so that we get a better quality of the part. So, a few more examples of the tooling here. This is a flow mixer. This is a test rig part to for testing some of the flow meters or any other flow devices. So this one, we can come out with a real innovative design using the additive manufacturing, by which we can reduce the cost, and then we can also reduce some of the back pressures which otherwise will be there with the conventional designs. Then there is a coating box. So this is the coatings which you do on the parts. So the fixture which is required for this coating. So the conventional design would have taken about 8 weeks, whereas we could do in additive in 2 weeks. So reducing the cycle time is the key thing, and then it's a better design from the assembly point of view. This is another good example of the rake, the measurement which measures the pressure across the airfoil. Typically, this takes a lot of time to make it through the conventional process. So, and it also involves a lot of welding, brazing, and then the EDM machining if you go follow the conventional process. The additive is the right way we can make this part and eliminate the welding, brazing, which helps in reducing the cost as well as the cycle time. So, and few more examples are shown here for the tooling applications. Typically, we can reduce the cycle time more than 4 weeks, and then we can also reduce the cost, and then we get a better performance from the tooling. So, since we are using additive for these toolings, we can take benefit of this additive. This is a typical applications for the conformal cooling applications. So, when we do the mold designs, we always keep in mind how that mold can be produced. With the conventional machining, we can always have the straight vertical or the horizontal or the holes. We cannot have the curved holes, and because of that, typically the cooling time is cannot be optimized. So in the pie chart here, you can see that uh, the, out of all the cycle time in the injection molding, cooling is the one which takes almost 50% of the time. What is shown here is in seconds. Cooling takes almost like 18 seconds out of the overall 35 seconds of time what this takes. All other process which is involved injection molding takes the remaining 50%. So this can be optimized by coming out with the additive manufacturing design. So we can come out with the complex informal cooling channels, which otherwise is impossible to produce using the conventional approach, which helps in the quality of the product by having a uniform temperature. It reduces the cooling time, so it increases the production rate, and then the tool life is also increases. We can optimize the design, and then we can validate it through the mold flow software, and then finalize the mold design. This is a practical example of deploying the conformal hybrid conformal cooling. This is for one of the safety devices, fire safety devices, what we are talking about. So the mold design was optimized by using the mold flow software, and we could get a reduced cooling time of more than 50% as part of this. And this design, you can see here the cooling conformal cooling channels which are incorporated so that we can quickly cool the mold, and then you also get the uniform temperature. So the process which is followed is we have the engineering team, which is the product design team, and then we have the AM team involved to come design these tools, and then the production agency which will implement this and then validate it. This whole thing was validated, wherein the production rate we could increase the increase by almost 50%. The 10,000 parts which were 5,000 parts which we were able to manufacture in a day, we could increase that to 10,000 parts in a day. So that's the validation of the things, and then we could demonstrate a cost savings of about 300K per annum as part of this part. So this is a good example of using conformal cooling for the mold design. The third topic which I want to touch upon is the using additive manufacturing for the repair and restoration. Uh, this is not a new thing which is already in use in many of the applications, could be automotive or for the marine components or for the aerospace components. We refurbish the part as a new conditions, and then it can have an additional life incorporated. Examples are for an automotive, it could be an engine block, or it could be some defects which would come into the engine blocks, and then that needs to be addressed. And or it could be marine components like the crank pin journal, where it could have a lot of cuts, ridges, and then the grooves, and then it needs to be grinded and finished. Or aerospace part like could be a landing gear, or a flight control actuators, or a gas turbine engine parts like a turbine blades or the compressor blades, which could worn out near the leading edge. So those are the areas where we can deploy this repair. Uh, the additive manufacturing technology for the repair, most of this uh, thing has been around the direct energy deposition, which is more like the laser cladding or the laser metal deposition, which has been in use for last 15 to 20 years. So that's what has been quietly largely used. But in the recent past, with a lot of improvements were happening in the DMLS or the EBM or the SLS technologies, the the powder bed fusion has been very quietly is been extensively used for repairing the parts, especially the complex parts. It is much easier and more can be done in a much more precise and an accurate way. And for the most of the plastic parts, FDM is the one which is used. Polymers are the plastics, so that's where yeah, those are the technology which are being used. So what we need to consider while we decide AM for the part repair. Uh, One is we need to decide which technology you are going to use it for repairing, whether it is a powder bed fusion or the FDM or the direct energy deposition. So that depends on the type of repair what you want to do, and then what capabilities each of these AM things offer today. We also have to keep in mind what is the material of the original part. Uh, Typically, we high cost new metals, and when you want to do it manually, the inefficiencies involved. So those are the parts which you consider it. So we need to keep that in mind, the both the product as well as the material which is feasible to do the repair through the additive way, and then how which material you are going to use for additively repairing the part. Today, these are the materials: Inconel 718, Inconel 625, titanium alloy, and then the stainless steel, aluminum. So those are the things which is possible today with the additive manufacturing. So we need to decide which material we are going to use to repair the part. We also need to decide on the AM machine itself, and then the settings, what is possible. So all those are the things which you have to finalize, and also you have to consider the geometric complexity of the part in making the decision of which is the best process and what can be achieved. Uh, in most of the repair activities, there's a pre-processing which is involved uh, for the object preparation, and then we have to do computational preparation to have the 3D model done. So in the object preparation, we need to prepare the surface on top of which you are going to build the part, and then we also need a fixture to hold the object onto the base plate. If it is especially a DMLS approach, then it has to be mounted onto the base plate and zeroed in properly, and then we have should be completely aligned. Uh, we definitely need to have a 3D scan of the existing part, which also decide it is superimposed onto the final product what we want, and then that will decide the repair which needs to be carried out. So this has to be very properly captured. A reverse engineering 3D scanner plays a big role in creating those models. uh, we also need to validate from the material compatibility point of view, from the microstructure, and then the strength, the durability point of view. So those are the questions which we need to clearly have the answers, so that repair process can be quickly approved and then certified. What are the challenges for the part repair using additive manufacturing? Uh, there are still a process gets evolved and then validated and then it is deployed. A few challenges which typically you come across while using additive as a process for part repair are uh, we need to build the model through reverse engineering. Uh, so that's the key thing, to capture all the details, and that's sometimes it needs to be it may create an issue in while building the part. Uh, then when you want to produce these parts, we need to have those some of those fixtures, and then the the machine and the CAD model, zero alignments in all the axes. So those are the things which we need to have some trials done before we can use it for the production. Material definitely is an issue. How good is the pairing of the object material and then the AM material? So if it is the same material, then the problem is little less. If it is a different material, then we need to understand the bonding between those materials and then validate it. And the material property itself, when compared to the base material, uh, on the AM material properties as well as in the property at the interface. So those are the things which we need to do uh, lot of testing and validation before we say that yes, additive is a thing what we can use it for repair. Uh, we also faced quite a few challenges in designing the fixtures to hold the part with the accuracies what is needed, and so the fixture needs to be flexible and adjustable so that we can address the challenges. So that could add a risk. So, but nevertheless, additive has been now very extensively used for many of the part repair activities, especially the worn out parts. May not be the safety critical parts, but all in all other areas, it's being very widely used. Uh, so you can see the uh, type of defects which you can see in a die and a mold in the picture. So those are the defects which we can repair it using the additive manufacturing and then fix it. So you can also see the tool insert here. One of the things what you can see is broken off here, and because of this, you have to completely discard the tool and then remanufacture this tool. Whereas in an additive way, you can rebuild that and then reuse it. So that's way it will decrease the downtime. It will reduce the cost. So that's what additive is helping as far as the tooling is concerned. The other way which the extension of this part repair process is the incremental printing which can be used. Uh, this is you already have a product, but that product in terms of the critical performance is concerned, it meets the customer requirements. But for assembling into the next level of assembly, it needs some changes. An example, what we are talking about here is the turbocharger. The turbocharger housing, especially the end flange, which gets assembled onto the automotive engine, that needs to be changed. But basic other features of the turbocharger is not changing. So this is typically made out of a casting, and to make a casting of this housing and then get that complete assembly done, it could easily take 3 to 4 months, even if tooling everything is available. So we can take the existing housing, chop off the existing flange, and rebuild on top of that what the customer wants, so that we can provide the customer demo very very quickly, and then he can do the custom assembly and then the initial field trials with this. So we could quickly provide this prototype to the customers in about 3 weeks of time, and then they could do the trials in maybe next 2 to 3 weeks, and then give that feedback. So that way we can also, it also helps to have a early customer engagement. So this type of incremental printing as an extension of the part repair technology could be very very efficiently deployed and then used to to create the differentiation with respect to our competitors. So with that, I will come to the end of this session. So additive is already playing a big role as far as its application for prototype tooling and part repair is concerned, and with lot of technology improvements happening in the area of metal printing to address the some of the challenges which may be there. It's going to be a big game changer in the next 3 to 4 years. So we can we can quickly come out with a product using the AM prototypes. Any of the tooling needs we can quickly address it, and then for the products which are already in field, we can increase that life through the part repair. So with that, I conclude my talk. Thank you. Thanks everybody for giving me this opportunity to talk about this next future technology. Thank you. Thanks a lot.